Okay, so today I'm going for the last class, I'm going to just scratch this article of Titchmarsh function of 1925, which Titchmarsh considers okay, functions. I said here the notation, this notation. These are functions f of z is integral ab f of t into the t z dt with f the function which is in L1. Okay, I use a Titchmarsh notation, so here there is not the I. So as a basic example, we already know the sinc function. So if you consider, for instance, f of z is equal to the integral between -1 and +1 of e to the t z dt, this gives e to the z minus e to the minus z over z, I guess, right? Which is like sine, well, I think hyperbolic sine of z twice maybe over z, which is like a sinc function, because okay, this has a zero exactly when I mean this is like a sine of minus I z, sine of minus I z over z, so it's like a sinc function, and this is equal to zero exactly when z is equal to some multiple k, an integer. So this is just to fix things, because we are interested in the zero of such function, and in this basic example, just to have the picture, okay, this is the real, this is imaginary, so we expect to find the zero here, and then last couple of Nikos lectures we had, so instead of having the real numbers, we have the imaginary numbers, and Nikos, the last lecture, talked about sampling and interpolating sequences of this kind, where we consider imaginary numbers. Okay, so and the problem is to understand understand the zero of f of this form. Let me put this zero of f of z, which is clearly a form of that function. Okay, so basically we will make the assumption. So let me do this. We make the assumption that f of 0 is equal to 0. This is not much loss of generality, because suppose that f of 0, so if f of 0 is equal to 0, we can integrate by parts. So we have f of z is equal to the say the integration by parts. So I take the integral of this one, which is an absolutely continuous function, have an integral between 0, a and t of x dx. Let's call this function here g of t times e to the z computed between a and b minus the integral minus the integral between a and b of g of x e to the some derivative of the z on top the t. So let's call this z times and let's call this function here t of z, and if f is in L1, okay, and this is 0, right? And this is 0 because well, at A this is 0, and also at B this is the integral between A and B. That f of 0 that we are assuming is 0. So my function f of z can be written as z times 0 z, where g is a function of the same type, and if f belongs to L1, then g is even better because it belongs to an infinity, so in particular is an L1 of the interval AB. And so I have reduced the order of 0 by 1 with this g, and I have a function with the same properties. Multiplying times z, it means that capital F and capital G, they have the same order, the same zeros, but for that is equal to 0, and I can do this several times until I get a function so I can write f of z to the n times some function a to z if h of 0 is bigger than 0, and this is still a function of this form here, for example. Okay. So we make this assumption that so what and another assumption that we make is that the interval is so first is that okay, this is kind of innocent. Then we also assume that the interval a the interval minus 1 1. Okay, here we need maybe be more precise because something we need in the following in the sequel. So it is okay. I can write so that interval a b. This is the midpoint. So I can write this f of z. I can write as the integral between a and b of f computed f. Okay, if t is here, it is can be written as the midpoint plus f times b minus a over 2 with s where this is t with x which is between minus 1 and 1, and so and the exponential becomes e to the x times b minus a over 2 times delta dx. Of course, there is this constant, and then there is a factor which is produced by this shift here, which is e to the a plus b over 2 times z. Okay, so this is like the Okay, so this function here has the form integral between -1 and 1 of some function, let's say, let me call this. Okay, this is the function h of the same kind, but where h is defined in b minus a over 2 times z, and we get an exponential over 2 times z on top, where this function h is defined as the form where this function h is a direct between 0 between -1 and 1 of some legal x equal as w the x and a equal 1. So that's about okay. So we will work with functions of this form here. Now the theorems that I hope to be, I mean, there are a bunch of things that Titchmarsh proved in this rather important paper. So, okay, so let's that n, like Rn into the I with n, this is 0 to 0 of x, where I assume that ordered by increasing quantity. Okay. So, what are the theorems? Theorems are, first, there. So, theorem 1 is the sum of 1 over Rn divided. In particular, functions in this of this form, they have infinitely many zeros. And theorem 2, it is that if I consider sum of cosine of theta n over Rn, this converges absolutely. So the sum of the real parts converge absolutely. And in the picture over here, it says that, I mean, not to be taken literally with these things, it means that here we have many zeros, and here we have scarce. Well, not many frequent. So there is we have infinitely many zeros. We have many zeros. So many to make these things divergent. But the the ones for which cosine of theta n is very close to 0, which is the ones which are closer to the imaginary axis.
Cos theta is small near to pi half.
Yeah.
So it's convergence it's near to pi.
Yeah, in fact, it is convergence absolutely. It means that
I think it's correct what you No, I think it's correct. This becomes small when the angle is plus or minus pi half.
right, yeah. Okay. Yeah. Okay, then there is a counterexample in which, I mean, he has an example which is theorem 3, which he said produces an example of a function which has infinitely many zeros here on the real axis. So, of course, they have to be very, very, very sparse. And in fact, okay, the number of zeros, and this is something which we will not prove because it requires some these are theorem 4. It is that if n of r is the number of zeros of moduli that is equal to r, then which is the quantity that weighs quantities of this kind of quantities make us talk about a trend, then the density of this thing can be computed precisely. It is n of r for this number of zeros. It is, as r goes to plus infinity, pretty much like b minus a over 5 times r. In fact, from theorem 4, we said we have so many zeros, it's easy to get theorem 1. This says that we have
to get the divergence. To get the divergence.
to get the divergence. Yeah, to get the divergence. Okay.
And this means that they are asymptotically equal. The ratio goes to 1.
Yeah. Yeah, that means that the ratio goes to 1. So it's an exact estimate.
The discussion we have in general about genus and order, so these are order 1. Yes.
Oh, I'm sorry. Yeah, yes, and I forgot. Thank you. I forgot an example. That what we want to have is that the interval AB is the best possible. Well, in this case, interval minus 1, 1. So I forgot this basic assumption that well, of course, if the function f is 0, then
So the closed support is
yeah,
is exactly minus 2. Yeah,
it is I forgot the sharpness of the interval AB in the general case. It means that if I consider the integral between a and a plus epsilon of modulus of f and also the integral between b minus epsilon and b of f are positive for all positive epsilon. So it means that you have some mass here and you have some mass here. You cannot. Sure.
That's essential support and related.
It's like
Essential support.
it is the closest interval containing the essential.
Yeah.
Yes. AD is the closest interval containing the essential support of 10. Okay. So let's go to the. Okay, so what is interesting? Okay, then there are other results. What is interesting, I think.
Sorry. So this is an assumption we made on F. So on the interval.
Why now?
You can hear now?
Yeah, I can hear.
So you couldn't hear anything?
No, they could, but maybe.
He asked something.
Okay.
Yes.
Oh, what is the question?
So the last thing we said is an assumption we made. I didn't get it.
It's an assumption which is the hypothesis
On the interval.
for all of these theorems. Yeah. Well, actually, it is a hypothesis for this theorem here, because the other two are kind of
Yeah, for the last theorem, I think. Yeah.
for this last one. Yeah,
Because then of course
it
it depends on the interval, so it is somehow the interval should be
So,
fixed.
okay. So now, what is interesting is the proof. And the proof is
Sorry, Nicola, I need 30 seconds to.
Sorry, the camera has been shifted, so I cannot see no more the left part. Okay.
Now it's okay?
Okay.
So when you shorten the interval, you have less zeros. So I guess also for.
when the interval vanishes,
Yeah.
you can
No, because you said this assumption is essential for theorem 4. Okay, but
for theorem 4. Yeah, because this gives an asymptotic estimate.
even if you have a smaller interval, you still have asymptotically this number but with a different quantity, so this divergence.
Right. Yeah. In fact, you get the same divergent, same result here, and I think you get pretty much the same one here. Yes, no matter whether A and B, but of course for this and some other results, you need more what A and B are. But also in the book, this comes. So okay. So what is very interesting for this course, it is that there is a heavy use of a Fresnel-Niger principle. So it's like an excuse to discuss it. So okay, before I say, and this is so there is an article 1908 which has been much expanded and so on. So this principle, this is an extension, a generalization of the maximum modulus principle or of the maximum principle. It says basically that if I have a domain and I have a holomorphic function or a harmonic or subharmonic, as we say, holomorphic function, which is bounded on most of the boundary, but for one point or maybe one set, let's say 1 point, then either this function is bounded everywhere on the domain, or it has to grow very fast when you go in direction of this point. Which means that there is a things can go bad, yes, but no less than something. It's like a dichotomy. Either they're good or they're very bad. Or very bad depends on the domain, depends on many things. So, okay, what we need it is this version here. So consider an angle. Consider an angle of pi over 2a in the complex plane. Let's call it t. Then we're here, and suppose that phi, the function is holomorphic in t. They continue, so one can relax some functions in t bar. Then suppose that this function phi has order rho, which is less than alpha, than alpha. But this it means that phi of r e to the theta. That's it. It's less or equal than e to the r to the rho plus epsilon for epsilon and for r, which are enough. Okay, and suppose that phi is bounded. So suppose that has order rho as in this, and suppose that phi of phi is bounded on the, of course, on the and phi of r e to the plus minus I phi over a bounded by a constant. Then, so it's bounded here that. Then phi bounded. Phi between constant in t. Which means okay, so it means that okay, the function is bounded here and here. So either it is bounded everywhere, or it has to grow bigger than order rho. That's what the statement says. Moreover, then we let use as a kind of corollary. If it goes to 0, so if we limit as r goes to infinity of phi over r e to the plus minus I phi over a equal to 0, then in fact the limit as z goes to infinity in t phi of z is 0. So if on top of these assumptions you have the function goes to 0 here, then it goes to 0 inside. So the proof basically by some comparison, we compare with the function, which is the function. Okay. So assume, so here there is a.
Sorry, Nicola, what is written limit for z tending to infinity and?
In t, in the region.
P in t?
T.
Who is?
So it goes to 0 here, and it goes to 0 here, then it goes to 0 here.
But is phi in T? Is what in T?
That,
Z. Ah, okay.
that.
Thanks.
Okay, so, okay, we said that we have rho, which is less than A, so let's pick a K between the two guys, and for comparison, we consider, omega z as the e to the minus z to the k, which is, okay, so this is a function so the modulus is like e to the, okay, the real part of that thing, the real part of that is r to the k times cosine of k theta, for that is always this one, which is less or equal than e to the minus r to the k. Okay, theta is less or equal than pi over 2a, so that's cosine of pi over 2, let's say over a, and k over a is less or equal than 1. So in particular, okay, this is a constant which is typically less than 1, if r for it is less or equal than 1, less than 1 r is bigger than 0. Okay, now consider for all, and this is the basic philosophy of this ferment principle. For all sigma bigger than 0, consider the function omega z to the sigma times f of that. Let's give it a name. Well, I will give it a name. 5. Function. Right. So, if I consider the modulus of this, homomorphic function, it is e to the minus r to the k times cosine k theta, and then there's a sigma, and that's sigma r to the k. That can be modulus of phi theta, but on phi of theta we have this assumption here on the order. So this is really like a big O of 1 times exponential of minus sigma r to the k cosine k theta, and this is plus r to the rho plus epsilon. In fact, here I could put as I did before this number here, 5 over 2 over 8 plus r to the rho plus x. Now, if I choose epsilon, so epsilon, if I choose epsilon, which is so that rho plus epsilon is less than k, then this goes to 0 as r rho plus epsilon less than k. For all sigma right? For all sigma bigger than 0, fixed. So we have that this is true, right? This is true for all that belong to T. And okay, and also since this function is less than 1, so this function omega z sigma phi of z, it is less or equal than c for z is equal to r plus minus phi over 8. So on the boundary of the region, sorry,
Sorry, rho P epsilon is less than.
Rho plus epsilon less than k. Rho plus epsilon less than k.
Okay, thanks.
So that this grows much faster than this one, no matter how these guys are small. Right. Well, I guess we're done because we have that. Okay, so we have that the function. So we have this function here. It is less or equal than c on the boundary of the region T, and it goes to 0 at infinity, so we can apply the maximum principle. But the maximum principle that says omega z the sigma other z is less or equal than c on T. Well, what does it say? This is
The modulus.
Yeah, the modulus. Yes. What this says, it is that let's say consider this one. It means that phi of z is less or equal than the modulus of omega z to the minus sigma, which is
You don't have to calculate it. You can just send sigma to 0.
yeah. For all sigma, and then the sigma goes to 0. For all z, right? For all z. Okay. About the moreover, okay, the complete proof is in the complete proof. It's in the notes, but let me just catch it. So assuming that the function goes to 0 on the boundary, so phi at r into the plus minus I phi over 8 here. So let me just put the pictures. So that means that we have a function. So it means that our function phi is 0 at infinity, and it is continuous and bounded. Well, it will. I'm sorry. It is continuous on the boundary, and it goes to 0 at infinity, and it is bounded. So that's my function phi, which has continuous on the boundary, goes to 0 on the boundary, and so on. But then I can change. I can change coordinates, so to make infinity here, I met this into the unit disk or the upper half plane, maybe the upper plane. So that infinity was here, and then the function phi psi. It is a function which is continuous here, and it goes to 0 over there, and it is bounded. Phi is bounded. Then using the usual argument, the argument that you use with the Poisson kernel to show that if you have a continuous function on the boundary that extends to a harmonic function which is continuous up to the boundary, you easily show that the unit. And that's up to your taste whether you prefer this or unit this, whatever the Poisson kernel you prefer, and using the boundedness, some triangular inequality and epsilons, and you have the as z goes to infinity. Well, maybe I should say phi psi as z goes to 0. That means upper half plane here, and this taken over there. Okay. Now. Okay. Now maybe if you agree, I will proceed with a couple of basic lemmas. Well, we are on the way of proving theorem 1. So the first lemma is rather innocent. I use the numbering of Titchmarsh, lemma 2.1, says that if f of 0 is equal to 0 for z, then the function leader f is equal to 0 for that's kind of okay. That follows from basic results of theory, because the hypothesis says that 0 is equal to f of I y, f of I y, it is the Fourier transform of y. Remember, it was the relative period between minus 1 and 1, or a and b, whatever, of I y dt for all y. But that implies that the function f, if f hat is equal to 0, then f is equal to 0. Here. By the way, a curiosity it is that, in fact, Titchmarsh proves it. So proves this Fourier theory result. I don't know if it, maybe it was not known before. The second one, it is that, okay, remember, we are this interval over there. It is that the modulus of f of r and theta, it is a little o, which is goes to 0, as r goes to infinity. R goes to infinity. Of e to the r time of theta, uniformly with respect to theta. Now, why is that interesting? But this is interesting by itself, because this says that, okay, here I'm going to explain. Okay. But for the case of the
Sorry?
X,
Below the little o, what's written?
as r goes to infinity,
R goes to infinity, okay.
which is that this quantity here over this quantity here goes to 0 as r goes to infinity, uniformly with respect to the parameter theta, which is that f of r into the epsilon over r cosine theta. That's equal to epsilon for all r greater than some epsilon and for all theta. Okay, so this says that no matter what is the angle theta, I take, I have that the function does not grow more than this thing over there. Well, actually, it grows less because it's a little off. So for the proof,
This is some kind of Riemann wheel lemma for all angles. On the imaginary axis is Riemann wheel.
right? Yes.
Fourier transform del one.
Yeah. Yeah, for the yes. Right, when theta, when we're on the imaginary axis, this says that the Fourier transform goes to 0. And that's pretty much what you can say about Fourier transforms of functions in L1. So the idea is that we want to apply Fermat-Lidl principle to this angle. That's what I call T. So it is the angle we saw before, which corresponds to the parameter A is equal to 2, because 5/4, 5/4. Okay, so here we have x, and here we have minus 1, x positive, 1 positive. I don't know why. Here, leave the lecture instead of because there is an L. Okay, okay, for x, so we're going to use a Frobenius principle over that. For x positive, for x positive, the estimate we do is, okay, we consider f of x. F of x is like the integral minus 1 of t x. And then we split into two parts. So we fix delta bigger than 0. And then we do, okay, most of the, okay, most of the interval, on most of the interval, we get, for this term here, we get the estimate e to the 1 minus delta x. On the remaining part of the interval, so between 1 minus delta 1, well, we are okay with the trivial estimate that this is bounded by e to the x. But then I choose the delta bigger than 0 so that d is less or equal than x. Okay. So fix epsilon bigger than 0. Then I choose delta so that the integral is 1 minus delta 1. There's an epsilon. Okay, that's okay. So this is less or equal, then let's collect this e to the x times, and here we have, well, worst possible thing, you have the L1 of this, times e to the minus delta x, and then here we have the plus epsilon over there, and this is less or equal than 2 epsilon e to the x, provided I choose x big enough so that this cancels most of that. So, so with this estimate for x, we introduce the function okay, so this is for the real x. And for the imaginary x, we have the f of this is like f of y, but this goes to 0 and y goes to infinity. That's for the Riemann effect.
Yeah, I said Riemann will.
Yeah. Yeah, I remember that. Well, RL. Yeah. Riemann Leffler. Riemann Leffler. Okay. Okay, so we have this. Moreover, I don't want to erase anything. Moreover, on the function f, we have that f of r e to the I theta. Well, the trivial estimate, it is that f of t, and then I have to put the real part of e to the z, which is e to the t r cosine of theta. Cosine of theta, we are here, so we are between 0 and 2. The t, which is bounded by some constant times e to the r cosine of theta. Okay. Now, we all have always exponentials on the right hand side. So consider g of z, just to cancel out the exponential z. So the modulus of this function it is, which is like in the general case, it's like e to the minus r cosine of theta times modulus of r theta. Okay, so this function here, it is bounded because of that, and it goes to 0 and x goes to infinity, because you see, if I do e to the minus x times f of x, that's less or equivalent to epsilon if x is large enough, which means that thing, and v of iy goes to 0 as y goes to infinity. So, okay, so this says, well, so we have the function is bounded, and it goes, function is bounded, where is function is bounded here, it goes to 0, here and there, well, it is continuous. Then, by the second part of Fermat-Linger principle, really, we do not use the Fermat-Linger principle, it just is plus on 3. It follows that G goes to 0. G that infinity D, but that's exactly the statement. Because if I do this goes to 0 uniformly, of course. Okay. Well, I did this on this order, and you know change times and things, and then you do on the other quarters. Now, lemma 2.3 goes in the other direction. So, because this lemma says that it does not grow. Well, it grows less. The function f grows less. Let me rewrite it. This says that fr theta grows less than e to the r and theta. So next lemma says that what you need is not of an exponential type, because it says that this is not controlled by e to the r cosine theta minus theta. matter of small delta. So for delta bigger than 0, for the theta real, this is not controlled by that. So it means that this has a there's a signal which goes to and this we get by contradiction. So we do two cases. The contradiction suppose that that's true. Suppose that f of r e to the I alpha is a bit O of r of e to the r cosine of alpha minus delta. And then we consider two cases. One case is alpha between pi over 2 minus pi over 2, and then another case is alpha plus minus pi over 2. Well, and all okay, this takes care of about half of the alphas, and the other half of the alphas can be taken very simply. Right. So, okay, so let's consider this case, and the idea is to use Mitter-Leffler. So that's case 1. Case 2, maybe a bit short notes. So the idea is to use Mitter-Leffler theorem here. But we do an estimator for cosine of theta is equal to 0. Then we do an estimate for theta is equal to alpha over there, and then we do Mitter-Leffler theorem here. This one goes up. Now, and the idea is to work with the function. So the idea we are in this first case. Consider the function g of z. The function g of z is well integral between 1 minus delta. But then when you do the calculations, you find that what you want to have is 1 minus delta over cosine of alpha. 1 minus delta over cosine of alpha of f of t is that t. And then you want to renormalize delta minus delta times same thing, 1 minus delta. Second. So consider this function here up to 1, which means that we only consider the function f over there. So the idea is to use
Sorry, what is the exponent? Cannot read. What is the exponent of the exponential?
Minus zeta times 1 minus same thing over there. 1 minus delta over cosine of alpha. Same which is down here. So the idea is to use fragment Linderoth to show that G is bounded. In the half plane, well, but the half plane, but then the other plane, then the G is constant. Then the G is identically 0. But if G is identically 0 by lemma to 1, that means that F is equal to 0 almost everywhere in the interval 1 minus delta over percent of alpha 1. But that's contradiction. Contradiction with the hypothesis that the function is not identically 0 almost everywhere on a small interval. Yes, that's at 1. Okay, so how do you get that? So if we so if you consider the renormalized version of lemma lemma 2.2, now remember you remind me what it is. So if you consider let's put a field of Z integral between A and B of S B e to the Z T. We said that this was renormalization was B minus A over 2 times Z times and then there was a shift factor with an exponential e to the A plus B over 2 times Z for there. Gives so for a function of this form where this is the function to which lemma 2 applies. But then I have this extra vector over there, and also it applies to this, but with this constant multiplying z. So you can easily check that this says, okay, there is a vector which goes to 0, and then you have something coming from here, which is e to the r cosine of theta times b minus a over 2. This was what we had in the lemma, but remember that we have this vector here. And then we have to take care of this vector here, which is e to the a plus b over 2 times r times cosine of theta. And this is the renormalized version of lemma 2. Now, we are in this interval here, where this is A and this is B. Okay, because our function G is a function, well, the integral, this is a function here. So now we have to take, okay, for this integral, we have to consider these two exponential terms. And then we have this extra exponential term over there. Okay? So for our function, we have that G of R e to the I theta is equal to, okay, we have the middle of 1 and R. We have this term on top here. Here we have R cos theta. So we have minus R. Let me copy because I don't want to make mistakes. Waste your time. Right. That's exactly that. Alpha. And then we have these other two terms, this and this, which is e to the r cosine of theta times b minus a over 2, which is b minus a over 2, which is delta second with alpha over 2 times e to the a plus b over 2, that's 1 minus delta second of alpha over 2 times r times the sine of theta. Well, okay, that's it. Everything would be nice if, okay, so if cosine of theta is negative, which is in this case, if cosine of theta is negative, then you see that everything cancels out. Because you have, okay, this and this cancel out, no problem. And here you get plus this minus, because that's negative, this minus the same thing, which cancels this one. So you get G of R e to the I theta is a leader of 1 and R. Uniform. For theta, okay, so we have that here the function not only is bounded, but it even goes to 0. If you go on the other, on theta is equal to alpha, here, let me calculate it. So for theta is equal to alpha, this one, we have that the integral, because we never used the assumption on the function f. We have the integral between 1 minus delta over cosine of r 1 of p into the here I guess well let me see that the modulus of that it is I do this. This is equal to f of z minus the integral between minus 1 and 1 minus delta. Alpha, the same thing. Now, for this term, we have this bound here on t. And for this term, we have the bound we had before. So, the first term is, by hypothesis, a big O of e to the r cosine of alpha minus delta, right? And the second term, well, I take the maximum value of the modulus of this one. What is left is the L1 norm of f. So it is a big O of e to the, and then I guess which is 1 minus delta secant of alpha times r cosine of alpha. Well, these two are the same things. These two are the same objects. So, okay, putting things together, right. These two are the same things, and they are cancelled by this one. Because this is r cosine of alpha minus r cosine of alpha times 1 minus delta secant of alpha. This is exactly the opposite. So this estimate here plugged into G implies that G of R e to the I alpha is bounded, but not. So this goes to 0. Here it is bounded. I have the right growth because the function G has order G has order left equal to 1. While remember that here A is equal to is less than 1, is bigger than 1. Because both angles, both this and this, correspond to some value of A. You need to less than 1. So we are exactly in the hypothesis. So I will use Mitter-Blatter theorem to conclude that G is bounded. And so bounded by constant. Well, okay, this way we show that G is bounded here, but we also have that G is bounded here, so G is bounded everywhere. So it's constant, but then it goes to 0 in some races, so it's 0. And then it decays alpha is equal to plus minus 1/2. I can just give you okay, when alpha is equal to 5/2, the idea is to use first Mitter-Blatter here to show that something has the correct bound there, but then we are in the case of just maybe I just will proof of theorem 1, and then we can close the course. So given all of these lemmas, let's prove that these functions are many zeros. But I wonder if I'm sure that some people study this, where instead of a L1 function, the distributions. But Okay, we want to put the sum of one over Rn. Now, suppose it converges, okay, by contradiction. Suppose sum 1 over Rn. If this converges, then we have bias factorization. Then bias factorization. Bias factorization reduces to the fact that f of z is equal to f of 0 times some exponential, some complex number and z times product for n 1 to infinity of 1 minus z over the n. Now, maybe I will show you what that converts to. Well, no, I think I did already. But we need something a bit sharp. Okay. So let's put this you know, okay, this thing here. Let's put this product with z. Now, the fact that I will show you later, it is that if this series converges, then this product here is less or equal than e to the epsilon z for all which is a product, a canonical product of this kind with this condition it is of some exponential type. So, assuming this fact, now we have lemma 2, 3. Which is about the lemma 2, 3 says that G of x, which is equal to G of x means this is equal to e to the minus, I'm taking x positive, e to the minus alpha x times f of x is not big O of okay, this is not a big O of what was the order well, it's here, but f of x is not of e to 1 minus delta x. We are in the case of cosine of theta equal to 0. Cosine of theta, sorry, theta is equal to theta is equal to 1. It's not. At the same, g of x is not a big O, g of minus x is not a big O of e to the alpha x times e to the 1 minus delta x. Here I consider indicator data minus 1. Well, but we take the modulus and the sign, so here the same thing. So that means that okay, compared with this one, it means that epsilon has to be bigger, greater or equal, well, bigger, greater or equal than 1 minus delta minus alpha for all delta equal to 0. And epsilon has to be greater or equal than 1 minus delta plus alpha for all delta. And this for all epsilon bigger than 0. Right? That's true for all epsilon. And that's kind of absurd because what we're saying is that for epsilon and delta bigger than 0, I want epsilon plus delta to be bigger than both 1 minus alpha and 1 plus alpha, which means that that both these numbers must be less or equal than 0. That's not possible. So in the last 5 minutes, let me sketch this vector. This vector is elementary somehow. Okay, G is this product over there. And we know this effect. So right. So when we write the logarithm here there, it is well, which is the sum of the logarithms of moduli of 1 minus that over n, which is less or equal to the sum of logarithms 1 plus 1 there over n, but that's what we call Rn. Rn. That okay, that thing. Now consider the function h of x, which is equal to this one, the sum of logarithm of 1 plus x over Rn. This function converges, and you can check that when you put, well, h prime of x, that's equal to sum. I have to do 1 over this one times 1 over there, which was there, 1 over Rn plus x. Okay. So this here is converted. This here is converted at the point, so this means that this function is differentiable and the derivative this one is something. And so and this goes to 0 by the way, goes to 0 and x goes to infinity by monotone convergence. So the punchline is that let me move with the graph. So this is x greater or equal than 0, okay. And then, well, and this is the function h of x over there. it is a function which is increasing and the derivative goes to 0, it means that for all epsilon bigger than 0, the function will grow less than epsilon at some point. And from that we get so the given factor is so for epsilon bigger than 0, there is some epsilon there, so that h of x minus a of x epsilon is less. So the increment here is less than epsilon times x minus x epsilon for all x bigger than x epsilon. X there. And that means that h of x is less or equal than epsilon x like constant or right that's an epsilon. And when you apply this function here, it means that g of x here in fact is less or equal we take the exponential to some constant times epsilon x, what is x? What is that? And okay, this is a very known fact, but we don't know.
Then does he prove it in the paper?
No, that's not. No, he says that product has this problem. Okay, well, it's over. Theorem 2 will be in the note, and all of the theorems are in Titchmarsh.
What's the name of the paper?
The paper is on something on Python. It is the theorem of certain integral function. Published on mathematics, not on. I don't remember. Published.
The theorem of, sorry?
It is the theorem of certain integral functions. But then maybe I will put the integral function. Okay, in the old times, you submit a paper on a journal, and then it was received May 1st, which is like yesterday, and read May 14th. So it took 14 days.
Great.
It was not to accept, not to accept. Read and you publish.
When he did this, probably he didn't have in mind the results of Ballerina. Because Ballerina results were from the 30s.
Yeah.
So it was something independent.
Yeah, some, there were some results, previous results by Poglia on zeros, but he cites. There are some results by Foglia, some of Landau. I think in a way, yeah, it seems that that he. I mean, it's curious that he proves that if you do Fourier transform of the function is zero, then the function is zero. Using the seed function, really. All right. So yeah, in fact, he does in this very special case. But that's true. Much bigger general. Okay. Well, guys, I hope to see you for.